Okay, hi. This is the third session for our topics on advanced mathematics. We have finished introducing abelian gauge theory and non-abelian gauge theory. Today, I'm going to talk about Dirac, Lagrangian, and Dirac equation, especially will introduce Dirac by spinor. The purpose is, of course, to prepare ourselves for the final introduction of standard model. Okay, all these topics are related to the standard model of particle physics. Okay, and today Dirac, Lagrangian, and Dirac equation are standard topics, and today I'm going to introduce these two concepts first by a very intuitive method, which is actually the original thinking process of Dirac. And then I will go next week, we'll turn to another way to introduce more mathematical, more abstract way to introduce these the Dirac by spinor. Okay, so today will be more pedagogical. I hope you will enjoy it. Remember, all the particles are spin 1/2 fermions. Therefore, we know that Schrodinger wave equation could not be to not apply to all the particles. And let me start with Schrodinger wave equation. And you probably have learned from quantum mechanics courses that how Schrodinger derived his famous wave equation. He first started with the non-relativistic energy momentum relation, which is p squared over 2m plus v is equal to E. And then he expected them to act on a plane wave, for example, in the form of exponential ip dot x exponential minus ip0t. This p0 could also be interpreted as omega, that is the frequency. And the momentum is interpreted as the 1 over wavelength. That's the typical relation of a de Broglie material wave. And then he made the quantum mechanical replacement of P with the gradient, or the partial derivative with respect to space coordinates. And energy is replaced with the derivative with respect to time. Because if you act this gradient over the plane wave solution, or the space derivative will give you a momentum here. Okay. Therefore, if you make this replacement, the relation energy momentum relation of a particle will be translated into grade square plus v equal to the partial derivative with respect to t. Of course, this is only a relation for operation. Therefore, it must act on something. That something here is, of course, the wave function. And if you put in the wave function psi here, psi here, and psi here, you got the famous Schrodinger equation. But how about a relativistic particle? Actually, Schrodinger originally started from a relativistic energy momentum relation instead of this one. I will show you why that project doesn't work for Schrodinger. As I say here, you can apply all these considerations to a relativistic particle. The only thing you need to change is the energy momentum relation. For relativistic particle, E squared minus P squared is equal to M squared. Okay, usually we write it as a 4 momentum square is equal to M squared. Okay, and therefore you can again make the replacement of P by the gradient and energy by the derivative with respect to t, we just plug in here and plug in here. Or you can also make it faster by using the covariant form, the covariant notation of relativistic mechanics. You just need to remember that the momentum and energy are part of a four momentum p mu, and therefore p mu could be replaced by the partial derivative respect to x mu, the covariant space-time, and therefore p mu replaced by partial mu. With this replacement, then the energy momentum relation p squared equal to m squared. Remember, p squared is actually p mu p mu. Therefore, this momentum energy relation could be easily replaced by partial mu minus m squared. Again, these are only operations, so they need to act on something. Here, that something, of course, is the wave function. Therefore, you arrived at a relativistic wave equation, partial mu psi minus m squared psi equal to 0. This is the original Schrdinger equation. I will show you why it doesn't work. But now it has been, because the Schrdinger did not publish it, therefore the next inventor are Klein and Gordon. So now this equation are called Klein-Gordon equation, the Klein-Gordon equation. I will show you how we are going to use the Klein-Gordon equation later. But let me clarify this equation one more time. Now we have partial mu psi minus m squared psi equal to 0. And therefore, if you want to see more clearly the physical consequences of this equation, you will want to expand the partial mu in terms of the time derivative and the gradient derivative. Therefore, this partial mu is actually partial square, partial t square, and this plus gradient square. Okay, and therefore this is the content of the Klein-Gordon equation. However, you may ask, why did Schrdinger not publish this one? The reason is that as a wave equation, it does not work. Why? First, it does not have a conserved probability density. Okay, so it takes a while to write down, so I'll just leave this statement here. However, there is another more relevant problem for us. This equation has a negative energy solution. It's quite obvious. When we solve this kind of wave equation, we usually plug in the plane wave. The plane wave consists of what I call exponential ip dot x times exponential minus ip0t. This is the plane wave solution. If you plug this into the equation, the second derivative, the partial square, partial t square, will give you p0 square. And the gradient square will give you p vector square, and equal to m squared times the plane wave. And the plane wave cancel each other. You are left with p0 square minus p vector square, and this combination is just the famous p square covariant derivative square. This must be equal to m squared. And therefore, this equation gives you a solution for p0. P0 now must be equal to plus or minus square root of m squared plus p vector square. Of course, you very immediately recognize this expression is just the energy, and P0 is the energy. That's exactly what we want. The P0 is the energy, and then this energy is related to frequency. So if you put it back, then this is the very famous plane wave solution for a wave. However, the problem is the plus and minus in front. The plus and minus means this P0 actually has two solutions, not just one. Okay, another solution is minus E. If P0 is minus E, then that means there is a negative solution, negative energy solution for this equation. That's very bad because we all know that the energy could not be negative. Otherwise, you can actually spend your energy and make yourself the state of your the energy lower and lower and lower and lower. Okay, so it's impossible. Therefore, that's at this point, Schrödinger at 1926 abandoned this equation, and he did not publish it. Okay, and then he turns back to the non-relativistic energy momentum relation. Okay, and but for this Schrödinger equation, you have already learned in quantum mechanics, there's no negative energy solution, because if you do the same thing as I did here by plugging the plane wave, then you got a relation P0 equal to V plus P squared over 2M. And therefore, the energy, the P0 only has one solution, or the energy has only the positive solution. Okay, so there's no problem with the Schrödinger equation. However, there is a negative energy problem with the now called Klein-Gordon equation. Okay, so that's why Schrödinger abandoned his original intention to write down a relativistic quantum mechanics wave equation and only reach the non-relativistic quantum mechanics wave equation. However, we now know that the proper way to interpret the Klein-Gordon equation is that it is not a wave function. Instead, it is a field equation, just like Maxwell equation. And therefore, the plane wave solution just corresponds to plane waves. And for plane wave, it's natural to contain a negative frequency components. Okay, so if you expand this Klein-Gordon equation by the plane wave like this, to have two different parts of the plane wave are actually very natural. For example, if you demand this phi to be real, then phi dagger is equal to phi. And then that gives you that this coefficient and this coefficient, remember this is the negative, this is the positive energy solution, this is the negative energy solution. And the coefficient of the second one is actually equal to the complex conjugate of the first. So you can write it this way. There's no problem at all, okay? And people have been dealing with this kind of mathematics for a long time. The only thing you need to do, again, is to treat the Klein-Gordon equation as field equation instead of a wave function equation, a wave equation. And you will encounter this kind of discussion in quantum field theory very soon, taught by Professor Chen. So I'll leave this solution to you, leave this solution at the moment, at here, and without going further into details. However, that's what we are ahead of the history. At that moment, Paul Dirac does not know this solution by quantum field theory. He still thinks he needs a relativistic wave equation. And his prescription is much different from what we did here. If you observe the Schrödinger wave equation, you will see that there's no negative solution, negative energy solution for Schrödinger wave equation. The reason is very simple, because here the time derivative is only the first order, and therefore when you plug in the plane wave, then you got only E to the first order. However, in Klein-Gordon equation, you got a time derivative to the second order. Therefore, if you do this derivative, then you got p0 squared or e squared. That's why you got the plus and minus sign. So Dirac put this negative energy solution problem into a mathematical problem. And therefore, Dirac set out to find a first order differential equation. Okay, so that's why I say here, Dirac blaming the negative energy problem on the second time derivative of the Klein-Gordon equation, and therefore he set out to find a first order differential equation for the relativistic particle wave. Okay, and however, on the other hand, this equation still needs to give the proper energy momentum relation. And therefore, Dirac proposed to factorize the relation. For example, let's illustrate this idea first in the rest frame. In the rest frame, there is no free momentum, only the P0. Therefore, in the rest frame, P0 squared is minus m squared is equal to 0. That's the usual energy momentum. Of course, here there is no momentum. The momentum, I should say, momentum is equal to 0. So that's the usual momentum energy relation. And Dirac proposed to factorize this relation into P0 plus mc times P0 minus mc equal to 0. And therefore, either this P0 plus mc is equal to 0 or P0 minus mc is equal to 0. But by doing this factorization, we got the energy relation in the first order of P0. Only one P0. And therefore, if you make the replacement, the quantum mechanics replacement by replacing P0 or E by the time derivative, then the wave equation would look like this. Psi, the time derivative of psi minus m psi is equal to 0. And this is a first order differential equation. That's the idea. Okay, so, and this equation, if you plug in the plane wave solution, it will satisfy this. And if you satisfy this, and you will satisfy this, the original energy momentum relation. Okay, so that's the idea. By using a first order differential equation, you satisfy energy momentum relation which is quadratic in P0. That's the idea. Okay, so now what we need to do is to do the same thing for any frame, not just the rest frame. That is, we now let the particle move and put in the three momentum P vector. Okay, so now the energy momentum relation is P mu minus m squared. And following Dirac's idea, we try to factorize this relation into two vectors. Each of them is linear to P. So I should say, Dirac proposed beta kappa P kappa minus MC times gamma lambda P lambda minus MC. At the moment, I think of this beta kappa as 4 constant and gamma lambda as 4 constant, but later you will see they could not be numerical. They could not be numbers, but that's the later story. I shouldn't go ahead of schedule. So let's say Dirac proposed to factorize this thing into beta kappa P kappa minus m times gamma lambda P lambda minus m. And therefore, we demand this relation is true and try to find the beta and gamma to make this relation true. And therefore, we need to expand the right-hand side into this form. This is this. So beta kappa gamma lambda times P kappa P lambda minus the cross term MC beta kappa minus gamma kappa. It is this times this and this times this P kappa minus Oh, sorry, this should be plus, but it doesn't matter. Oh, sorry, I think I should change this one of the sign. For example, here to plus. Okay, that's a minor mistake. So it will be minus m squared. So this minus m squared and this minus m squared will cancel each other. And for this relation to be true, we will need this term to vanish, because on the left-hand side, there is no linear term. Therefore, beta kappa minus gamma kappa must be equal to 0. That means beta kappa must be equal to gamma kappa. So beta and gamma are actually the same thing. We need to choose the same numbers, the same constant number. And the first term will need equal to each other. Therefore, beta gamma and gamma lambda must be equal to this. Okay, must be equal to this. However, in the first equation, I have already known that beta and gamma are the same thing. Therefore, I can replace this beta in terms of gamma. Therefore, I arrived at P mu equal to gamma kappa, gamma lambda, P kappa, P lambda. Okay, and it's easier, so we need to solve this equation for gamma. Remember, we want to solve the gamma number for this relation to be valid. And it's easier to write down in detail. Okay, for example, the left-hand side is this, and I can write down all the left-hand side is this, and I can write down all the terms. There are a lot of them, but it's not that difficult to write down all the terms. For example, you got the gamma 0, then this must be P0, then you got the first term. And you also have cross term, gamma 1, P1, gamma 0, gamma 1, P0, P1, and that is here. Okay, so you can work out all the mathematics and algebra yourselves, but this is what happened here. And from the relation, you can easily see that for the two to be equal to each other, gamma 0 must be equal to 1. Gamma 1 squared must be equal to 1. Hence, we got the gamma 0 squared equal to 1, and gamma 1 squared, equal to minus 1, because there is a minus sign here. Okay, so gamma 1 squared is equal to minus 1, gamma 2 squared and gamma 3 squared are both equal to minus 1. And then all the other cross terms must vanish, because on the left-hand side, there are no cross terms. Therefore, gamma 0, gamma 1 plus gamma 1, gamma 0 must be equal to 0. So, and all the other terms are the same. That means gamma mu plus gamma mu must be equal to 0 for mu and nu that are not equal. Oops, how could it be possible? Remember, the second equation could not be satisfied by any numbers. For numerical numbers, they always commute, but the second equation told you that they do not commute. I should say they actually anti-commute, because if you put this term onto the right-hand side, gamma nu is equal to minus gamma mu. So we call this kind of relation anti-commuting. And we all know that the number could not anti-commute. Okay, so here I write down some of the examples to let you see it is impossible. So Dirac concluded that no numbers could accomplish this. But however, that's the genius idea of Dirac. Dirac proposed all these constant gamma could be true for matrices. How about we propose this gamma to be matrices? Then it is not hard to find matrices that anti-commute. That's the genius idea. Well, at this moment, nobody knows what do we mean by a matrix equation. However, mathematically, this is possible. So Dirac proposed it. Okay, so it's really a daring way to do physics. Without the only evidence for doing all this is, remember, the desire to arrive at a first order differential equation, and secondly is the energy momentum relation. These are the only two foundations for Dirac to build this very, very daring adventure by asking that maybe this equation should be written in matrix way. If this relation should be written in matrices way, that means the wave function needs to be columns instead of just a number function. That's a big jump. That's a big jump. So the wave function we finally arrive at actually is a column instead of just a wave function like a Schrdinger equation. Okay, so what kind of matrix could accomplish this by giving you the gamma mu, gamma nu anti-commuting? Actually, it's not hard because for 2 by 2 Pauli matrices come very, very close. Pauli matrices is these three matrices we always use in electron spinor, the spinor property in electron. And we are now trying to find out the electron equation, wave equation. So therefore, using these two matrices are not very, very strange. So this is sigma 1, this is sigma 2, and this is sigma 3. And it's famous from the quantum mechanics courses that sigma I squared is equal to 0, is equal to 1, exactly what we need here. Remember, gamma 0 squared equal to 1, gamma 1 squared, gamma 2 squared, gamma 3 squared are all equal to -1. And these three matrices anti-commute. Sigma I, sigma j is equal to 0. You can check by yourself, okay? And therefore, by combining these two relations, we can write sigma I, sigma j, the anti-commuter is equal to delta ij. However, it does not work because there are only 3 of them. Remember, we need 4 of them. Gamma 0, gamma 1, gamma 2, gamma 3, because we are talking about space-time. There are 4 dimensions. Therefore, 3 Pauli matrices, even though it comes close to the relation we want, it does not work because we need 1 more. Okay, so Dirac say, actually, I think mathematically he can prove that it is impossible for 2 by 2 matrices. But Dirac find it, so the next you should try probably 3 by 3. And Dirac probably prove also mathematically it is impossible for 3 by 3. So the next step, of course, is 4 by 4. And we indeed find 4 by 4 matrices, 4 by 4 matrices that satisfy the relation we want. Okay, here is the solution. Gamma 0 is 1 minus 1, 0, 0. Gamma I is 0, sigma I minus sigma I, 0. These 4 matrices are called Dirac matrices. And you can check by yourself. For example, if you square this gamma 0, of course, it is equal to 1. Okay, and it takes more algebra to prove to yourself gamma I0 is equal to -1, but it does work. And you can try to find out the anti-commuting relation, and I will leave it as an exercise for you. Well, it's easy to just do it on a piece of paper. That actually they satisfy this. Okay, so Dirac find it is possible for 4 by 4 matrix to get 4 matrices that satisfy all the relation we need. And these relations are summed up into this very covariant form, gamma mu anti-commuter equal to 2 G mu nu. Okay, you can check by yourself. These are the same thing. Okay, so with the invention of the Dirac matrices, we get a very beautiful relation, the p mu minus m squared. Remember, this is a number, could be factorized into matrices. Okay, however, but if you expand these matrices, and you can go back to the relation here. Okay, that's the idea. Of course, when you multiply matrices by matrices, what you get is still a matrices. However, you can check by yourself that it is a diagonal matrices, and it is equal to this times 1. Okay, probably I should write this more clearly. It is this relation times I, because the right hand side still needs to be a the right hand side still needs to be a matrices. Okay, that'll be better. Okay, and if the p squared, p mu minus m squared equal to 0, that's the energy momentum relation, then it will imply one of the factors must also equal to 0. Okay, therefore, we pick the first order factor like this one and write it in terms of gamma mu p mu, just like here, gamma mu p mu minus m times c equal to 0. And then we make the usual replacement by p mu with the derivative with back to x mu. P mu replaced by this, then this equation becomes I gamma mu partial mu minus m equal to 0. Of course, again, it's an operation. It needs to act on something. But what else could we put in instead of just the wave function? Therefore, we put in a psi, we get this equation. Ladies and gentlemen, that's Dirac equation. I gamma mu partial mu psi minus m psi equal to 0. Dirac equation. Okay, again, let me emphasize, in this derivation, Dirac only relies on one relation, which we know is the energy momentum relation of relativistic particles. Okay, and of course, he insists that the wave equation must be first order. And with that in mind, the only way to accomplish it is to factorize this energy momentum relation into two factors. And the genius idea here, the breakthrough, is he realized that the factorization does not need to be numerical. It could be in terms of matrices. And that makes you a Dirac equation, which is actually a matrix equation. Okay, so this gamma is 4x4 matrices. If gamma is 4x4 matrices, that means this psi must be a 4-component wave function. We usually call it psi 1, psi 2, psi 3, and psi 4. And because spinor has 2 components, so this new wave function are called bispinor or bispinor. You will learn in quantum, after quantization, after you put this Dirac equation into the quantum field theory and quantize it, you will learn that these 4 degrees of freedom actually corresponds to the spin up and spin down particle and antiparticle. So 2 by 2, that give you a bispinor. Okay, but I'll leave it to Professor Chen to teach you that in quantum mechanics. At the moment, it is a bispinor wave function. Bispinor wave function. Okay, so here I write down the expand this very covariant form into a form that's easier to read the physics. This Dirac equation could be written as gamma 0 partial psi partial t plus gamma I partial psi partial xi minus m psi equal to 0. And therefore, Dirac equation is not just one equation because psi has 4 components. Okay, so this Dirac equation actually consists of 4 equations. Okay, so this is the Dirac equation we finally arrived, and then and Dirac then start to try to solve the equation. Again, I'll leave it to Professor Chen to teach you about how to solve a Dirac equation, etc. But now, before I let you go, I would like to remind you something very interestingly. Okay, that will be very, very related to what we are going to talk about next week about the representation of Lorentz group. That is the observation that actually this relation could be accomplished if m squared is equal to 0 by 2 by 2 matrices. In the argument I just gave you, this is impossible for 2 by 2 matrices. However, it's not totally true. If I ask that the fermion has no mass, then the massless fermion actually we could write a 2 by 2 matrices if there is no mass. Let me show you how to do that. Okay, so again, let me start with this relation by factorizing p mu minus m squared, the energy momentum relation, into 2 factors, just as we did before. However, now I expand the right hand side. It's this. That's what we already did. But now I ask that the mass equal to 0. Then this term disappear, this term disappear, this term also disappear. So we got only one term. However, remember, without this term, I could not claim that beta and gamma should be the same, right? Okay. Originally, in our original argument with mass, because the right-hand side does not have a linear term, therefore this term must vanish. So beta equal to gamma. But here we don't have a mass. This term does not appear in the relation. Therefore, we don't have the argument that beta and gamma need to be the same. So supposedly they could be different things. So presumably beta does not equal to gamma. So this relation, I should write it correctly, p mu equal to beta kappa gamma lambda times p kappa p lambda. And we now can choose beta as 1 sigma I and gamma as 1 minus sigma I. You can check by yourself. By plugging this relation into here, actually this relation is satisfied. Actually this relation is satisfied. So that means with the new beta and gamma, then actually this and this, the 2 factors, could be different instead of the same as in the original case. Okay, and therefore this factor will give you a wave equation like beta mu partial mu psi equal to 0 and gamma mu partial mu psi equal to 0. Okay, so that means for 2 things. First, the massless fermion contains half the degree of freedom of the Dirac particle. Okay, because now beta are only 2 by 2 matrices. Therefore, the psi is a 2-column wave function. Secondly, we now have 2 wave equations. This and this. Remember, beta is not equal to gamma. So we have this for one kind of particle and this for another kind of particle. Okay. This could also be seen from the Dirac equation itself by using something we call gamma phi. Gamma phi. So I forgot to put in the relation. Yeah, so maybe I'll do this the next time. Okay, yeah, I will do this the next time to show you the gamma mu, the gamma phi. Okay, so today I'll probably stop here, but remember here I have proposed to you that actually the original. So today we did two things. First, we get the Dirac equation. We get the Dirac equation. Now, Dirac equation is for a bispinor because it has the wave function has four components. So if a spinor is two component, so that's why it is called bispinor. But on the other hand, we can, if the mass is equal to 0, actually the two component spinor could also work. Okay. On the other hand, we could have two equations. Okay, we have two equations. This will be the starting point. We are going to talk about how we can arrive at the bispinor Dirac equation next week. Okay, so let me start here, and I will see you next week to talk further about how to derive Dirac equation in a more mathematical and abstract way. Okay, so stay tuned and we'll see you next week.